I welcome each one of you to the online webinar lecture conducted by Saint Philomena College, Puttur. This webinar lecture will be given by Dr. Divakara Mayya, Professor, National Institute of Astrophysics, Optics and Electronics, Mexico. He will be speaking on stellar evolution and structure of galaxies. Friends, we are in the most difficult time. Corona, invisible, lifeless, tiny virus has created havoc and made we people the life a misery one and locked in the room and office and our place. But it is also opened a new opportunity and the human spirit to alive to face the challenge. One such effort is the possibility of online teaching and the knowledge sharing. Hence, the Saint Philomena College Physics Department has arranged this webinar lecture. Now let me introduce Dr. Divakara Mayya, my good friend. Dr. Divakara Mayya is professor in the Institute of Astrophysics, Optics and Electronics in the other part, that is in Mexico. A village boy with intellectual brilliance, hard work, dedication can reach greater heights. There are many examples like APJ Abdul Kalam, former President of India. Dr. Mayya is one such example. He was from Tingaladi village near Puttur, hardly 6 kilometers from the college, Saint Philomena College. He studied at Saint Philomena High School, PUC and BSc and Saint Philomena College, and then MSc Physics from Mangalore University in 1986. In fact, we were the classmates from 6th standard up to MSc. Mayya did PhD in Indian Institute of Astrophysics for the thesis Star Formation in Giant Extra Galaxies, H-second regions, and then postdoctoral in the France probably, and then joined Institute of Astrophysics. Mayya has almost 3 decades of research experience, and he is one of the frontline experts in the galaxy dynamics. His research interests are star formation, history and population synthesis, extragalactic star clusters, ring galaxies and their evolution, lenticular galaxies and their origin, and he has published more than 50 research papers in the top-notch journals such as Astrophysical Journal, APJ, Nature, and monthly notices of the Royal Astronomical Society letters. And under his guidance, 6 people obtained a PhD and 2 are working. And he's a brilliant lecturer, and I welcome Dr. Divakara Mayya, and the baton will be given to him. He takes over. And it is the time span, and it is a morning, a beautiful morning in the India. At the same time, it is the evening in the Mexico. Probably it is around 10 o'clock in Mexico. Over to Mayya.
Okay, thank you, AP Radak, for the nice introduction. I would like to say that I don't reach anywhere near Abdul Kalam. I have a lot of respect to him. Well, so your intention I appreciate. So I really welcome all the students and other participants for this webinar lecture. So I'll be giving it on stellar evolution and structure of galaxies. So as AP mentioned, I graduated from St. Philomena College, so I have very nice memories of the college. And in fact, that's where I got my physics and mathematics basics. That basics is the stepping stone for whatever I achieved later on. You know? So now I'm full-time dedicated to a career in astronomy, and I hope with this talk I can motivate some of you to think about physics as a career opportunity. And you can do that, only you have to keep resolving your questions until you get the right answers, and those answers had to be based on some solid theories. That's my advice to you. So without spending more time on this, I will start straight away on the topic. So that is the stellar evolution. Actually, why this topic is still important, I will show historically how this topic developed. It's more than 100 years old, actually, but it is still relevant, and it affects the structure of galaxies. So in the background, what you see is patches, the white and dark patches. That's what we generally call as Milky Way. Actually, as I'll illustrate the next page, it's the center of the galaxy. The entire thing you see in this image is the Milky Way. Every star you see in this image is every star belongs to the Milky Way. Milky Way has around 100 billion stars. 100 billion, it's a huge number. So in this image, you don't even see millions of stars. So, and when you look at the sky, you may think that there is nothing between stars. Actually, it's not true. There are a lot of material between the stars. We call it interstellar matter. This material is basically a very diffuse gas and few grains of dust. In this image, you see these dark patches. These are basically dense clouds, and in these dense clouds, stars are formed. Stars are continuously getting formed. So, thanks to the presence of this kind of dark clouds. If you zoom in on any of these, any part in this galaxy, you will start seeing other structures, which are the building blocks of galaxies, structures such as star clusters and nebulae. Now, I will show some examples immediately. Well, let's first see how a galaxy will look like if we were living in another galaxy. It can't be, we can't do intergalactic travels. We have sent satellites. I mean, the satellite that has gone farthest from the Earth is Voyager, which has left the solar system. So we are nowhere reaching another star, actually. So we can't see our galaxy as though we were looking from outside. But we can have a guess of how it is by looking at other galaxies. For example, here in the left side, Andromeda, our neighbor, we believe it's a galaxy very similar to the Milky Way, and also another galaxy which has a number in the Messier catalog 81. So we believe that, the problem with getting a photo of our own galaxy is that we are inside the galaxy. So being inside, we can't know how the structure, the global structure is. So what is done here, in the right side, you can see what we imagine as the Milky Way. So that is the effort of more than 100 years of studies by more than 1,000 astronomers. All this information has been put together, and even using the information that we have in other galaxies to create a map. It's a reconstructed image of how a Milky Way would look like. How the Milky Way would look like. So we believe it has some 4 spiral arms. With these structure which look like spirals, we call it spiral arm. And our location is around 25,000 light years from the galactic center. The whole galaxy measures around 4 times the size of the distance between our sun and the center of the galaxy. So look, now we are, and this structure is a very thin structure. It's a spiral galaxies are a 2-dimensional structure. Basically, all the stars are confined to a very thin disk. So what happens when we are looking at in the disk towards the galactic center, we see everything projected onto the plane of the sky. And at the top of this image, where I probably can see the cursor, you can see how this whole image would look like if you project it onto a single edge-on view. So actually, in the middle, you can see where the telescope is there, how the Milky Way looks in the sky. This is the real image, taken in this case in the La Palma Observatory in Spain. So this edge-on view is very similar to what we see in this photo. So we can understand that what we call colloquially as the Milky Way is actually the disk of the Milky Way seen from the edge. And there are galaxies, like in this case NGC 5907, which looks very similar to this edge-on view. So the thing to remember here is that the sun is somewhere in the middle between the galactic center and the extreme edges of the Milky Way. Okay, so I mentioned about the nebulae. If you zoom in on any part of the galaxy, you can see other structures. I won't talk much about these structures in this talk, but I will just show some of these images. On the left side, you have what are called as star clusters. It's one of the fields I work, so I'm extremely interested in these kind of objects. So there are two kinds of star clusters: the open cluster, which have typically thousands of stars, and they are open in the sense they're extended. And also we have very concentrated globular clusters. They are very concentrated, with the sizes very small compared to the open clusters, and they are symmetric. They have spherical form, and typically these kind of objects can have million stars in a very small space. So to get an idea, between us and the nearest star, that's a Proxima Centauri, you can have many thousands of stars in this, if you live in the center of one of these clusters. So dense are these clusters. Well, on the other images you actually see in this page, they are basically the nebulae, and there are many nebulae in our galaxy, and all of them can be put into one of these categories, one of these 7 categories. On the left, you see what is called as Herbig-Haro objects. Actually, these are objects which are discovered where I work. In the 1950s, we have in our observatory we have a telescope which we in these years we don't use, but in the 50s it was one of the leading telescopes in the world, with the Smith camera telescope, discovered a lot of objects by our institute founder called Guillermo Haro. That's why these objects are named Herbig-Haro objects. So these signify very early phases of star formation. Actually, star is the red spot in the bottom of that figure, which were not known when these objects were discovered. They didn't know what is the cause of these supersonic jets. Actually, these are what we see are supersonic jets. Then we have what are called as dark clouds. So these are the regions where stars really form. And reflection nebula clusters. This is actually Pleiades cluster. We can see by simple eye. So it has it's somewhat after star formation, you see some of the gas around, so which reflects the light, and then you have these baubles, which are or emission nebula, which are associated with the high mass stars. Some of I will discuss later on during the stellar evolution these structures. And the planetary nebulae and supernova remnants are the final phases of low mass and high mass stars respectively. So let me straight away go into the topic. The main topic that I'm going to talk today is regarding the stars. So let me see first whether what colors. Let me convince you that stars have colors. I don't know how many of you really appreciated the night sky, and have seen the colors of the stars. This is the Orion constellation, which is in the winter you can see is very nicely, and the brightest 2 stars, Betelgeuse on the right top and Rigel on the left bottom, are contrasting colors. One is red and one is blue. And if you see in this image, it's a deep image. All the faint stars, most of the faint stars are red. So stars have colors, and let's see what is the origin of the color. Well, in 1910, 2 astronomers, Hertzsprung and Russell, independently plotted a diagram which from that time is known as Hertzsprung-Russell diagram, HR diagram. This is the most important diagram in astronomy, and it is our day-to-day tool to work. It's like It's like for you, most of you, you can't live without probably mobiles. It's like for astronomer, you can't live without, we can't live without this diagram. No? It's every day we work on this diagram. So there are several versions of this diagram. So the most, the version that is used by Hertzsprung and Russell has what is known as a spectral classification in the x-axis, which is denoted by letters O, B, A, F, G, and K, and M. Okay, the stars, I will go into that a little while later. So, and on the y-axis, you have what's called a luminosity. Luminosity is defined as 4 pi distance square multiplied by the flux. The flux is a measurable quantity. Simply, a brighter star has more flux, fainter star has less flux, and the luminosity depends on the distance. So to create this plot, you need to find the distance, and these scientists had obtained the distances for all the stars they had plotted. Well, what they found was 90% of the stars they had fell onto a very narrow band, which we call as main sequence, which is diagonally running in this diagram. And the remaining 10% are located in the other 3 branches called the giant branch, supergiant branch, and the white dwarf. I'll go into detail each one of them as I go along in my talk. So you can note that the Betelgeuse is the star which is at the extreme right, top right. It's one of the coolest stars and the brightest stars. Whereas the Rigel, other bright star in the Orion constellation, is blue, and it's one of the brightest stars, not only in the sky, but even in its absolute magnitude. It's very luminous. So actually, the sequence of color, this diagram is color coded. You can see that the stars on the left side are blue, meaning they're hot. On the right side, they are cold and they're red. So, which means the spectral classification O is indicating that stars are hot. Actually, they have around 30,000 Kelvin temperature, whereas cool stars have around 3,000 Kelvin. I'll soon relate this how the spectral class is related to temperature. So actually, the order of this color is exactly like the colors in the rainbow. You have Vibgyor sequence, the violet in the extreme left, whereas the red color in the extreme right. And all the main sequence stars basically have this tendency. The brighter stars are bluer, and the redder stars are really cooler. So everything's okay? You can hear me?
Yeah.
Okay. Yeah. So yeah, just confirming. So okay. Well, why there is a relation between the color and the temperature? Well, the answer was given way back in 1900 by the black body radiation theory by Max Planck. Earlier, Wien's theorem was already there. Max Planck gave this formula: S nu is equal to 8 pi h by c cube into nu cube divided by exponential h nu by kt minus 1. Magic formula which explains why stars have color. For example, a star having a temperature of 6,000, like the sun, will have a spectrum as indicated in this diagram at the topmost curve, and it will emit most of its radiation in the yellow color. I didn't mention the previous diagram. The sun is located in the yellow sequence of the colors. So, whereas if the stellar temperature is lesser and lesser, reaching 3,000 Kelvin, it mostly emits this radiation in infrared. It can be still seen in the optical by our eye, but it's brightest in the infrared wavelengths. So you can extend this this formula to any temperature you want. So that's what is there in the inset in the top right, where it's extended up to 10 to the 5 Kelvin, for example. where most of the radiation will be going into the extreme ultraviolet or including X-rays. On the other hand, there are very cold particles having just 100 Kelvin. So their emission will mostly go in the far infrared wavelengths. So the same formula applies to a very wide range of electromagnetic spectrum. And even more important, the formula only has the temperature as the variable. It doesn't matter whether the emitting source is a star or emitting source is a brick or a carbon or even gold. It only depends on the temperature and nothing else. So the same formula can be applied in the laboratory as well as for the stars. So this explains basically why hotter stars are bluer or ultraviolet, emit most of the radiation in the ultraviolet, whereas cooler stars emit in the infrared. Okay, the next relation that we talked in the HR diagram is the relationship between the temperature and the spectral classification of stars. I have packed a lot of information in this page. I will remain for some time in this. So, well, let me start with the right part where you can see really the observed spectra of different stars classified as O, B, A, F, G, K, and M. This classification, rather the ordering in this sequence, was done by Annie J. Cannon in Harvard in 1912. So earlier classification was all A, B, C, D, F without any physical meaning, and she thought that there is some temperature information there and very intelligently arranged in this order. Although at that time there were no physical equations to relate it to temperature. The prevailing equation was the Boltzmann's excitation equation, which was developed much earlier, where the temperature is there, and that equation tells us the probability of exciting at different levels given a temperature, and the energy levels of the different levels, energy difference between the levels. So, but the formula cannot explain the presence or absence of different lines. So in this spectra, you can see that hot stars emit lines of hydrogen, whereas cold stars emit lines of sodium, magnesium, oxygen, and many other lines. M stars are filled with the many molecular lines. So this tendency cannot be explained by Boltzmann equation. So the problem was solved by Saha, Saha from Calcutta. So Meghnad Saha's equations gave you a means of understanding these spectra. So the equation relates the probability of having an ion in atom in a given ionization state, given the temperature and the ionization energy of the ion you are talking about. The psi is the ionization energy. So with this formula, you can exactly see why helium atoms are seen in very hot stars, because you can ionize them, whereas helium cannot be ionized in the cool stars, so you can't see that. So the absence of a line in a spectra doesn't mean that the atoms are not there. It could be there, but it's not in the right conditions to show this line. Well, finally, the entire calculations were done by another great lady scientist, Cecilia Payne. Actually, it was her PhD thesis in 1925, who explained exactly this pattern, which is shown here in this diagram. So, as a function of spectral type, she could exactly see which are the ions that are present, and hence their lines can be seen in this spectra. So this completely resolved the issue, and in fact her conclusions were not accepted, because the conclusions were that the universe is mainly made up of hydrogen and helium, including all the stars, including sun. So that was not acceptable at that time. It was done in 1925, because Earth doesn't have hydrogen and neither helium. So how can stars have something that Earth doesn't have? So the idea was that stars also should have the same elements that we have in Earth. So it took years to get the acceptance to this idea, and now we know that that is the truth. 90% well, in mass, it's 70% of the universe's mass is in the hydrogen, and around 26% is in the helium. That is the present knowledge that we have. Okay. Well, we saw that the stars can be treated as black bodies, but what is the really observational proof for that? Well, you have here this relation between the temperature and the color. Well, color, well, usually we associate color by what we see by eyes. It's some subjective thing. So, well, subjective thing cannot be used in science, so we should be very objective. So we define colors by a quantitative means using this formula, which is color in two bands, B and V, the blue and visual bands, can be defined as the logarithm, 2.5 logarithm of the flux in the B band and flux in the visual band. So this the equation for these fluxes can be black body. When you apply the black body equations here and plot as a function of temperature and color, you get this the thick line. You can measure also the temperature using the spectral type showed earlier, and you can also measure the color using observations using filters. So that's what is shown. Sun is an yellow star. Sun is a yellow star which has around 6,000 Kelvin temperature, and which has a color of around 0.5, which is yellow. Yellow is in this index is around 0.5. So which exactly sits on the curve. Same way other stars like Betelgeuse and Bellatrix also fall on the curve. So this is a very nice illustration that stars can be approximated as black body. So here in the right I show you that there are violet stars, there are all these different stars, and just by measuring the color of the stars we can know what temperature the stars have. Okay, so let me talk about the stellar energy source now. So stars, now we know that shine because of nuclear reaction. So it took time to appreciate the stars really are atomic bombs. The nuclear reactions take place inside the centers of stars. So nuclear reactions derive the energy because by combining 4 hydrogen atoms, you can form one helium atom. But the mass of the 4 hydrogen atoms is more than the mass of the helium atom. And this difference in the mass, also called mass defect, is converted into energy using the famous Einstein equation. And that's what is finally liberated as radiation, as electromagnetic radiation. And that's what keeps stars shining. So the first person who really showed that you can produce the energy seen by the sun using these reactions is Eddington in the 1920. So using this kind of chain reactions, you put in 4 atoms of hydrogen and finally get an atom of helium, but you get out of some gamma ray, some neutrinos, and all these things. Well, after that, it took some time. Well, these reactions can only produce helium, but we know that on the Earth we have other elements. Somewhere they should be prepared in the universe. So later it took in 1950s the work of Fred Hoyle and Margareta Burbidge to completely resolve the creation of elements using other equations. So incidentally, Margareta Burbidge died last month. She was at Caltech, died last month at the age of 99. And so she was the pioneer in solving the nuclear synthesis of higher elements in stars. Well, then we have the famous alpha beta gamma theory, where they use these Eddington's equations to show how the primordial helium is produced. So that was also a success. That was done in 1948. So now we know that all the elements in the universe are produced in stars. Well, almost all. some require very special condition for their production, and it is still a very active field of research these days. Okay, now, I will now move into describe the stellar evolution. Actually, stellar evolution is mostly called as life cycle of stars. Actually, it's a cyclic. You born the stars, and stars are born, they evolve, and before evolving, they create enough space for forming new stars. So it is a cyclic process. Star formation can be, the evolution of this life cycle can be described into 6 stages. Well, first stage I call incubation. It's basically where stars are formed. They are molecular clouds. And molecular clouds, once formed, within a million years, they give rise to stars. In the very densest regions of these molecular clouds, you can create conditions for the fusion reactions, and that's the definition of a birth of a star. So this here, the dark clouds you see, these are the places where such densities can be reached. Well, as soon as they're born, they start shining, but then the dense material completely blocks the radiation. You can't see it at least visually. So, but if you have infrared eyes, or we have infrared telescopes, you can see stars completely embedded inside these molecular clouds. That's what is shown here in the left bottom diagram. These are images taken using infrared telescopes. Well, generally, so this is, we call it stellar nebulae, where stars form. And once stars are formed, it could be a solar, like yellow star, or it could be a massive star like Betelgeuse. If a star is like sun, so it follows a particular sequence, and if it's massive like Betelgeuse, it follows another sequence. A sun will be a red giant and eventually finish as a planetary nebulae, and leaving behind a white dwarf as a stellar remnant. Whereas if it's a massive star, it will be a red supergiant, which will explode as a supernova, leaving behind either a neutron star or a black hole. So the path taken by the star or its final product depends on only on the initial mass, nothing else. It depends only on the initial mass. Well, why is that? To understand that, let's see the time scales of all this evolution. On the left side, we have this another version of the HR diagram, a temperature versus the luminosity, where you see the main sequence, the diagonal band. In the sun, the yellow star, at the bottom right, lives around 10 billion years. So it can keep on transforming hydrogen to helium for 10 billion years without having any change. That's another property of these stars. When they are in the probably I'll go back. I forgot to go through this. Okay, 90% of the stars spend their time as main sequence stars. That is, they just keep on burning hydrogen to helium. That we called as youth. And during the youthness, they don't have any change. No? Humans, we change from childhood to adolescent to adult. We keep aging, but the stars, once they're born, they're exactly like that. No? It's like probably like butterflies. Butterfly is born and dies exactly with the same size. No? So stars are like that. Once they're born and until their death, nothing changes. So, and that time can be 3 million years for very massive stars and several giga-years for stars like the sun. No? Whereas once they run out of hydrogen, then they reach the old age, and then that's where they form as giants and supergiants. There can be variable stars also in these processes. No? Finally, they die as supernova in like a flash. It's much smaller than 1 million years, the time period, and they leave behind the stellar remnants. And these stellar remnants actually live forever. You know? It may be contradictory. They are dead stars, but they never die again. You know, they will be there forever as stellar remnants because they have stable configurations. Okay, so what is the reason that the massive a star is, it lives less time? It may be counterintuitive. We usually expect the bigger it is, it has to live for higher time. No, it is exactly inverse. A star like Sun can live for 100 billion years, whereas a high mass star like a 30 solar mass can only live for 5 million years. Well, the reason lies in this diagram in the middle top, where I show the reaction rates or the efficiency of the principal nuclear reactions. Basically, there are two ways of burning hydrogen to helium. The one of the process is called proton-proton chain, the PP chain, and the other one is the CNO cycle, the carbon, nitrogen, oxygen cycle. Well, the second procedure requires some trace of carbon, nitrogen, and oxygen as a catalyst. What the reaction is, what's happening is that you prepare helium from hydrogen through reactions involving carbon, nitrogen, oxygen, as is shown in this here in the bottom. So you have carbon, which has 12 its atomic weight, combines with the proton, generating a nitrogen, sorry. So and so on, and finally it creates a helium atom and gives back the 12C. So it is just used as a catalyst, and you can do it same way. If there is nitrogen, you can create again similar kind of reactions. So in the first stars this reaction cannot happen, but now the Milky Way and the universe has these elements, so this is also a viable process. Well, the reactions efficiencies are extremely temperature dependent. The PP chain dependency is less than the CNO cycle. CNO cycle and the reaction rates for the two reactions are the same if the temperature where the nuclear reaction is taking place is 18 million Kelvin. 18 million Kelvin. It happens that if the stars have mass less than 8 solar masses, you can't reach these temperatures. So it means only the PP chain can happen in these kind of stars. But if the stars have masses more than 8 solar mass, then the CNO cycle will take place, and that's much more efficient, and that liberates even more than 1,000 times more energy than in the PP reactions. So what happens? In the massive stars, the reaction produces more energy, and the available energy is finite. That depends on the mass. So you can lifetime is basically depends on how much energy is there divided by how much luminous the star is. Luminosity is energy by second. So you can play around this number and finally calculate that a 30 solar mass star in mass is only 30 times bigger, but in luminosity it is 10 to the power 5 times more luminous than Sun. So getting lifetimes of only few million years. So that's why massive stars live very short. So there are stars up to 150 solar masses. These 150 solar mass stars can live only a 1 million year or less. Actually, that is very good for us. I mean, otherwise there wouldn't be human beings in the universe. There cannot be life in the universe because these massive stars are the ones who produce the heavy elements like iron, calcium, magnesium. Everything is produced in the heavy high mass stars. And if they lived for giga years, then all this produced material will be locked inside the stars. It's good that they die explosively like supernova, and in that process they released all these elements, cooked elements, into the interstellar medium, and the interstellar medium gets enriched by these heavy elements, and the Sun is formed in one of these nebulae enriched by these heavy elements. So that's why on the Earth we have all these heavy elements. Only with the low mass stars you can't produce these heavy elements, as we'll see later. Well, here is a table where you can see the lifetime for different stars. It's well, to compare, the age of the universe is 13.7 billion years. So you compare a star of 0.8 solar masses lives 17 billion years. So which means even the first star of this mass that is born is not yet has died, because all stars that are born are still somewhere in the universe, whereas there are stars up to 0.1 solar masses of mass, and their lifetime is 1 trillion. So they will keep on burning hydrogen because their rate of burning is very, very less using pp chain. So they will never finish whatever hydrogen they have in their nucleus. So that's the important thing here. Okay, so now let me go into some details. So how these reactions take place? Well, as I showed in the previous page, 8 solar masses is a very important mass limit, because if it is larger than 8 solar mass, then you will have CNO reactions. So in the low mass stars, which means mass is less than 8 solar masses, only pp chain will take place in such stars. So such stars will be 90% of the time they will be in the main sequence, and then they will move along this sequence, which are called as the subgiant branch, to red giant branch, to horizontal branch, to what we call as asymptotic branch stars, and next to planetary nebulae, and to white dwarfs. Well, there are different names, don't worry about that. So basically, if you can see my cursor, so this is the way the star will evolve. So at the end of the AGB, so it will be a white dwarf. So let me show you the internal structure of the star in 2 phases. First, when it is climbing up the RGB branch, this red giant branch. So if you peep inside the nucleus, so the nucleus has a helium rich core. All the hydrogen has been burnt, and you have deposited a lot of helium into the core. And when it is climbing up, but here the temperature still is not good enough to burn helium into higher elements like carbon and oxygen. So helium is contracting, whereas there is a shell where the temperature is good enough to burn hydrogen that is there in the shell into helium. So that produces energy, and that expands the star, and that's the reason why it's going up. Its luminosity is increasing. So basically, eventually the temperature will rise in the center, where helium will start burning into other elements like carbon and oxygen. That happens in what is called the horizontal branch. It is similar to the main sequence branch, where hydrogen is burned to helium. In the helium branch, horizontal branch, you have helium burning into carbon and oxygen. Well, after that, what happens? It is shown in this plot on the top right side. So finally, you have produced what is called as the asymptotic branch, or AGB star, which is very big in radius. And if you peep into the nucleus, so nucleus basically has a core that contains basically carbon and oxygen. So in this core, the temperature will never reach to further to take place further reactions. So that will remain as a inert carbon oxygen core. Whereas in the outside, there is helium still burning, and hydrogen can burn even in layers much outside. So this is the typical structure of a star just before it goes into the planetary nebula stage. So the central portion where the carbon and helium core is there, that is basically a white dwarf. Now this white dwarf right now has the shells of other elements covering it, but because of the radiation that is coming from this hot nucleus, slowly these shells get dispersed into the interstellar medium, and that's what we called as this planetary nebulae. You can see the star, if you are good enough, there is, I don't know your resolution of your screen, you can see a very small point in the center of this planetary nebulae. That's basically white dwarf, and the entire structure that you see is the was once part of the star, and that has been expelled, and that has been that's expanding, and in few thousands of years this will disintegrate into the surrounding interstellar medium, leaving behind this naked white dwarf in the center. Then we'll call it that a white dwarf. So white dwarf is basically a carbon-oxygen core. Basically, it has only carbon and oxygen and nothing else. Whereas if the star has more than 8 solar masses, so it can again have two kinds of sequence. We know that they will finally die a supernova, but just before dying a supernova, it can be a red supergiant star like the Betelgeuse, or it can die as Wolf-Rayet stars. I'll briefly talk about Wolf-Rayet stars at the end of my talk. So the cutoff mass here around 30 solar masses. If that is if the star has more than 30 solar masses, then you can have Wolf-Rayet phase just before the supernova explosion. Well, what is the nuclear structure? In this kind of stars, since the overlying weight is too much, so after the once you get the carbon and oxygen core, here the overlying weight can further compress it and increase the temperature to form heavier elements. So the carbon will be burnt into neon, sodium or magnesium, and the neon will be burnt into again oxygen, magnesium, and oxygen will be burnt into silicon and or sulfur, phosphor, and finally the silicon will be burnt into iron, cobalt, and neon. Beyond iron, you can't have fusion reactions because iron has the minimum binding energy, and you have to the reactions after that, they are not exothermic, and you can't have nuclear reactions producing elements more than iron. So finally you end up with the iron core. You can't get nuclear reaction further, so the star will have an iron core, and the overlying material will compress further and further the iron core, and you can't have nuclear reactions, and what happens is it goes on compressing, and finally the density increases so high that you get really nuclear densities. To start with, you have iron atoms. What will happen? The atoms will break, electrons will separate from the atoms, and finally the protons and neutrons will all combine. As the pressure increases, the protons will capture some electrons and convert it into neutrons. Finally, we'll have only neutrons in this core as the pressure increases. Actually, what we are producing here is the neutron star. Well, if the density is too high, it cannot be a neutron star. It will be finally a black hole. Okay, so the structure, external structure around this neutron star or whatever neutron core is onion-like shells. You have silicon bonding shell, you have carbon bonding shell, you have helium bonding shell, you have hydrogen bonding shell. The structure difference between a red supergiant and a Wolf-Rayet is that Wolf-Rayet has a lot of energy coming inside, from inside, which peels off these outermost layers. The hydrogen shell is completely peeled off, and even the helium shell getting peeled off. So you start seeing the elements recently produced. You start seeing carbon and oxygen in the spectra of these stars. Where a red supergiant star has this hydrogen shell, which prevents us seeing the internally produced elements. Well, what is the time scale of all these reactions? It's curious. If you compress the entire time scale to 1 day, 24 hours, let's say yesterday midnight you started your reaction, and up to 10 o'clock in the night, to be precise, 10:24 in the night, it will be still burning hydrogen to helium. And next 1 hour, 35 minutes and 53 seconds, it will be burning helium to carbon and oxygen. We have only 7 seconds for producing all these remaining elements, and actually the iron is produced in the last 30 microseconds. So this iron core, as soon as produced, if you normalize really to the time, it is less than a few days actually. So less than a day actually. It's only a few hours. The entire iron is produced in the last few hours of the life of a red supergiant or a Wolf-Rayet star. Okay, so now I explained what is the internal structure of these compact objects. So, and I also have said that we have three kinds of compact stellar remnants. Well, white dwarfs have size of the Earth, around 6,000 kilometer radius, but they have a mass of 1.4 solar masses. That's the maximum mass. Well, this maximum mass was derived by Chandrasekhar, who did this calculation, which is shown in the plot here, which is basically the evolution of the radius as a function of the stellar mass. Again, the contrary to intuition, the radius decreases as the mass increases. As the mass increases, radius decreases. Usually, it's not the case. The stellar mass is higher. Usually, you have higher radius. But when the objects are like compact objects, stellar remnants, the relation is inverse. Higher the mass of the star, smaller the radius. And using quantum mechanics and relativistic astrophysics, he derived a upper mass limit of 1.4 solar masses for the white dwarfs, which until today stands. These values are derived in 1930. Curiously, he derived all this. He created this graph in the famous ship that he took to travel from Madras to Cambridge, where he did his PhD degree. When he arrived in Cambridge, he already had this very interesting relation, and which earned him the entire fame. So this is the upper mass limit for white dwarfs. Whereas if the mass is higher than 8 solar mass, so as I said, you can have neutron stars. And again, neutron stars are supported by the quantum mechanical degeneracy pressure of the neutrons, and they can have masses up to around 2.1 solar masses, and they will have a radius of around 10 kilometers. Imagine, as one entire mass of 2 times the mass of the sun dumped into a size of a city, around 10 kilometers. So this actually inside the neutron star, the structure will be like a crystal, so reaching extremely high densities that can be material like quark, gluon, plasmas in the centers of these neutron stars. Well, the third object, compact object, the black holes, that will have masses more than 2.1 solar masses, and the radius. Well, you can't define a radius to black hole because it's a singularity. You have entire mass packed into a point source. What we can define as a radius is actually a quastral radius. That's the radius beyond which even light we cannot see. Now it's the last light scattering surface called as the event horizon. So that is the radius we give for around the black hole. Well, until last year, these were all theories, but this image, the color image I show, this is the most famous image of the last year, so which was obtained by a combination of many telescopes, including our telescope here in Mexico. This is the image of the event horizon of a supermassive black hole in a galaxy in the Virgo cluster. So you can see here, what you see here is the event horizon, and inside it's black, meaning that really there is event horizon. So that is the first image of really a black hole. Why it was so difficult to get? Because the size is so small that you can't resolve this image. They're so compact, and the there are no nearby objects where we can resolve this size. So now we have observational confirmation of really telling that there is the event horizon, and even inside the event horizon, that's really black. Okay, so now that I have explained you the evolutionary theories, let me talk about the success of the evolutionary theory. In the beginning, I said the whole universe depends on the evolution or evolutionary theories. So all the phenomena we see in other galaxies and all, we explain finally using the evolutionary theories, which are mostly verified in our galaxy, in the Milky Way. One of them is the simple one. So we can explain the positions of all stars in the galaxy, in the chart diagram, as I illustrated earlier. So we can explain the position of Betelgeuse, we can explain the position of Rigel, and so here in the middle you have a theoretical evolution of stars. All these lines here, blue lines, for example, is the evolution of a 15 solar mass star, so which passes through Rigel and it will reach up to Betelgeuse. So we know that by other means that the stars, these really have like 12 solar masses of mass for the Betelgeuse. So this evolution tracks exactly produce the observed properties. Same way other bright stars like Capella, Arcturus, Aldebaran, they are like products. They are in the red giant branch, and when they were in the main sequence, they had around 2 solar masses of stars. Also, evolutionary theory explains exactly the position of the variable stars known as Cepheids. There are 3 kinds of variable stars. One are called RR layer variables. Other one is called the Cepheids, Cepheids of type 1 and type 2. Cepheids are very important for cosmology and for all the astrophysics because they give a means to measure the distances to galaxies. They are bright, so they can be seen even in other galaxies, and the technique for obtaining the distance is that their absolute luminosity depends on the period. So larger the period, they are brighter. So just by measuring the period, we know how bright they are intrinsically, and by comparing with the measured brightness, we can obtain their distance. So that is the technique that has been employed to obtain distances to many galaxies. Okay, the second point I'm talking about here is about the recent variability of Betelgeuse. I don't know how many of you have heard it, but in December and January and February, until coronavirus took us to only talk about coronavirus, this Betelgeuse was in the news every day. So Betelgeuse, as you know, is the star, bright star in the Orion constellation. It is as bright as the Rigel, the blue star. But suddenly in December, this star, simple with the naked eye, we could see that was dimming every day. So it dimmed by around 1.6 magnitude. The interest was here. The interest was that it's a red supergiant. After the red supergiant, it will explode as a supernova. So interest was that whether it will explode as a supernova in our lifetime. So, well, it can be there like that 1 million years. It is almost, but it can still wait 1 million years before it exploding. But since it was dimming, that was the interest. But the news now is that as time went on, so from around 1st November 2019, it started dimming. This is the light curve. So, and reaching the faintest magnitudes in the beginning of February. After that, it started again brightening, and now actually it is brighter than what it was earlier. If you have now you can't see Orion constellation, so you have to wait for a few more months. So that it is actually brighter than what it was. So it has recovered completely its magnitude, and actually, if you compare the historical brightness of the star, always it was varying, but in the last 40 years, so it has never reached the as dim as we saw in February. So it is really dimmed, but it has recovered its magnitude. So for now, it won't explode in our lifetime probably. So we know the reason for that. The reason is that well, this is one of the few stars for which we can take an image. Usually stars are so compact that you can't resolve them, but this being a supergiant and not very far, so you can really take a photo of this star. So in the beginning of 2019, last year, so this was the picture of this star, but when it was dimming, one side was not seen. So what is happening here is that looks like the star has expelled one of its layers or some part of its layer, and that was obstructing the light. So that's the reason for this dimming. So it's like some dust, some cloud passing in front of the star, which dimmed the star momentarily, and as the cloud moved away, so we don't I mean, it has recovered its magnitude. Okay, my another topic of I'll continue another 5 minutes. So I'll see the watch that it's around 1 hour now. So the greatest success for me is this. The stellar evolutionary theory can be used to understand the universe, especially to know the age of stellar populations in other galaxies. So as illustrations, I have some graphs in the left side. So well, the star clusters are aggregations of stars of all same age. So you have hundreds or millions of stars, all of the same age, and we know that more massive a star is, less period it lives, less time it lives. So what happens? As the cluster ages, you get rid of the most massive stars. So that's what's happening here. A little slightly aged cluster will start losing these massive stars, and cluster evolves more and more. So the most massive stars will be little lesser mass, and finally it will reach this kind of form. So theoretically, we can predict how the HR diagram will look like as the cluster ages. I have some examples here. The famous Pleiades, which you can see by naked eye, has the HR diagram of this form. If you compare with this figure, so it exactly matches the figure here, so which corresponds to a cluster of around 100 million years. So just by making this diagram, just by measuring the color and the magnitude of the star, so I can know what is the age of this cluster, thanks to this all the developments in the stellar evolution. I have another extreme example of a cluster, globular cluster of 12.3 gigayears, so which corresponds to this kind of plot. So we can see it's a chart diagram where you have only the sun-like stars as in the extreme bright in the main sequence, and most of the other stars are along the giant and in the horizontal branch, as expected from theoretical calculations. So fantastic! The observed properties match what is predicted by the stellar evolutionary theories, and then we can imagine that these clusters should be host to lot of these compact objects, pulsars, white dwarfs, and black holes. Should be there in the centers of these. As I told earlier, once they are formed, they will remain there forever. Well, what are the consequences of this? Well, I'll talk about the consequences. Briefly, I will talk about the implications in the extragalactic universe rather. So, which is regarding the galaxies known as starburst galaxies. So, especially a galaxy known as known as M82. It's one of my favorite galaxies. I've worked a lot on this galaxy. So this galaxy is known to have a biconic structure. This is the observed image where you can see some biconic structure in the vertical direction compared to the disk of the galaxy. Well, if you zoom in on the center, you can see a lot of these patches. Actually, they are stellar clusters. Each point here is a stellar cluster. Each one can have thousands of stars inside. So imagine now you have hundreds of several hundreds of massive stars. Hundreds of stars are massive, and all of them will explode as a supernova, at the time. So the energy released by this event will be huge that you can't contain that within the galaxy. So it will be like a balloon. This is the theoretical explanation. So it will be like a balloon. It will start blowing up to a point where it cannot hold. The pressure inside will finally pierce a hole in this balloon, and the material will be launched into the halo. That's what we see. So this is another consequence of this all the stars evolving simultaneously in this kind of clusters. Okay, so the last topic I'm giving here is the challenges for the stellar evolution in the future. So there are very interesting hot topics now. So one of them is the gamma ray burst. It's almost half a century since the gamma rays were discovered, but it's only in the last 2 decades that we know for sure that they're galactic objects. They are of stellar origin, not galactic. They're stellar origin. So which means stellar evolution has to produce them. But in the scheme that I presented, there is no gamma ray burst. So we have supernova, but we don't have gamma ray bursts. Well, there are 2 kinds of gamma ray bursts. One are very short duration gamma ray bursts. The burst lasts for less than 2 seconds. Luckily, gamma ray telescopes are always viewing the entire sky, and anywhere a flash occurs, they can register and they can measure that the flash is less than 2 seconds in some cases, and some cases it can be more than several seconds it can be. So these 2 are considered two kinds of gamma ray sources are considered now as having different origins. The long duration gamma ray bursts are thought to be due to the Wolf-Rayet stars. I mentioned that Wolf-Rayet stars are staged just before the supernova explosion. But Wolf-Rayet stars, since they start losing their outer layers, so they form some bubbles, like what is seen in this right-hand diagram. So this bubble keeps going, but imagine when the supernova explosion occurs, it can eject a powerful relativistic jet, and the jet, if it pierces through this the bubble material, theoretical calculations have proved that they can produce gamma ray emission. Gamma ray are extremely energetic radiation, and that is the only way right now we know how to produce this kind of burst. So we know that it is related to the Wolf-Rayet, but still details are missing. That's one of the challenges for the stellar evolution, to produce this gamma ray bursts. Well, the second kind of gamma ray bursts that have short duration, so they are produced using the black hole mergers, or neutron star mergers. So as you see here, the 2 black holes very close by, they can merge together, and in that event they can produce gamma ray. But in this event, they not only produce the gamma ray, but they can also produce what are known as gravitational waves. That's the second exotic phenomena that I am describing here. So the gravitational waves are discovered now around 3 years ago. using this one of them as LIGO. So the telltale signature of gravitational waves is the plot I have in the right side, where over a very short duration of time you get these pulsations. You can see the whole duration is from like 0.45 seconds, less than a second. Within less than a second, you start seeing the oscillation, and finally oscillations stop. By measuring exactly the amplitude of these oscillations as well as the frequency, you can exactly predict what kind of compact object should have been merging there, whether it's a black hole, or black hole, neutron star, or neutron star mergers. Right now we have, I think, several, more than a dozen of such gravitational waves detected. So here I have an example on the left side where you see the masses of the merging objects for each of the detected gravitational waves. So the top mass is the fusion product, whereas the bottom, in each one of them there is a there is an arrow. So two stars merge to produce the top one, and in all these cases it is the black hole mergers. In all these cases, black holes have between 5 solar mass to around 15 solar masses, producing objects up to around 80 solar masses of black hole masses. So same way, you have stellar remnants. Neutron stars can also combine with these black holes and form this kind of gravitational waves. So I'm putting here again the picture of globular clusters, because as I described earlier, globular clusters should have lot of these stellar remnants, very nicely packed. They're very dense. So they are the fertile grounds where you merge these kind of objects. It's important to note that although the entire process of merging takes less than a second, but to reach to get that close two of these objects, it takes more than 1 billion years. So it's a slow process, but once it reaches a very short distance, then it can merge very rapidly. So these are kind of objects, since they are more than few billion years old, so they could be the places where gravitational waves can be detected. Well, stellar evolutionary theories right now does not include binaries. All the scheme I narrated is all as the stars are in single stars. There are recent theories including binaries, and still a lot of parameters involved while you model using the binaries, and that's one of the future challenges to produce these two kinds of exotic phenomena directly using the stellar evolutionary theories. I think with that I stop. So I will thank you very much for being with me all this time, and thank you, and I can accept questions now.
Dr. Mayya, there are some questions in the chat section. For example, are the gamma ray bursts measured mainly which are having very high energy?
Okay, so I'm seeing the question, so
Yeah,
I'll go with the order there.
Yeah, probably it can give the.
Okay, whoever wants to ask the question directly can also ask. Okay, so are these gamma ray bursts measured mainly which are having very high energy? Well, gamma rays are of high energy. So I don't. Well, GeV. Gamma ray bursts are measured in several GeVs. Basically, it depends on the telescope that's operating. They are measured using the ground-based telescope as well as some of the satellites. So basically over a large range of energies in the gamma rays. Second question. Is there other questions? Yeah. There's a question. Tell me something about LIGO findings. Well, I just presented as products of stellar evolution. So on the LIGO itself, I don't know much about it. So I prefer not telling more about the LIGO. But if you have questions directly on related to stellar evolution, I can answer that.
Now, regarding the structure of galaxies, whether these black holes exist at the center of all galaxies?
Yes, good. Right now the prevailing idea is that black holes are there in all galaxies, in the centers of their galaxies. No? Well, in this talk, since I talked about stellar evolution, so I talked mainly about stellar mass black holes. No? So whereas there are other black holes known as the supermassive black holes that have masses more than 1 million solar masses. No? So these cannot be produced by stellar evolution. So they are born when the galaxies are born, and as the galaxies grow, their masses also grow. So that the prevailing idea is that in all galaxies you have these black holes, but for example, in the center of the Milky Way, the black hole has a mass of around 4 million solar masses. So that's the current status. There is a question. Explain strain versus T graph. I don't know which graph is mainstream.
There is Mayya, in the Facebook, there is a question from Gauri Panikavitiri. How was the gravitational waves measured?
Again, using this LIGO observatory?
Yeah, probably.
Yeah. How do we locate the position of black hole in space? So black holes, as the word says, you can't see the black holes, no, directly, but you see because black hole cannot be quiet. You can hide it. If a material goes close to the black hole, so that will attract that material. So before that material falls into the black hole, so it gets heated up, and the friction heats the gas, and that heated gas emits usually in X-rays. So we have X-ray telescopes operating which detect these kind of phenomena. That's why much before this last year's discovery of this image of the black hole, we knew black holes exist, because a lot of X-ray sources which you can't explain by other phenomena. So somebody is asking me to explain the last one. This one. Sorry, AP, you asked something?
Someone has asked how to take the photograph of the black hole. The photograph of the black hole is taken, and what are the techniques are used to take the photograph?
Yeah, so that is right now only 2 objects are there in the entire universe, I can say, where you can take the picture of the black hole. No? So that the limitation comes mainly because of the limitation of the size of the Earth. So we have a telescope called Event Horizon Telescope that is as big as the diameter of the Earth. No? So there are telescopes in Antarctica, and there are telescopes in the north of the US, so which measures basically the diameter, and the larger separation is the telescope, you get into higher resolution in angle. So since these objects are so small, you need extremely large angular resolutions to resolve and take the photograph. So this is the telescope, and the telescope that obtained it's not telescope, it is the project that obtained the image involved like 7 telescopes spread over the United States, one here in Mexico, which our institute controls this telescope, and other telescopes in South America. So combining the signals of all these telescopes, each telescope has a precise time measurement. They have atomic clocks, and later all these images are combined to produce this map, taking information about when exactly the image in each telescope is taken, and by processing this image was formed. It's a very tedious, computer intensive image, and you can't get it every day. So the image that was obtained was of, as I told, it was in the Virgo cluster, the elliptic galaxy in the center of the Virgo cluster, and the other source where such images can be obtained is the center of the Milky Way. Observations have been already taken, and the results are not yet announced. Soon we'll get some news on that. So these are the only 2 objects where the sizes and of the event horizon is big enough for them to be resolved. Okay, any other question?
There is also another question regarding the neutron stars and regarding their exceptional magnetic properties.
Okay, good question. I didn't mention about that. Actually, I didn't even mention the word pulsars. So neutron stars have lot of magnetic fields. So this is because they are only 10 kilometers of size. So to start with, they had radius much bigger than the sun. So you have to conserve the magnetic field, and they are rotating also. So then if you calculate to conserve the magnetic field, so the magnetic intensity turns out to be around 10 to the power 12 Gauss. In the Earth we have less than 1 Gauss, so it is 10 to the power 12 Gausses of magnetic field in the neutron stars. But neutron stars, although they have magnetic field, they rotate, and all neutron stars rotate. So, but the magnetic axis is aligned with the neutron stars, then you can't see these neutron stars. But if the magnetic axis and the rotation axis have an angle, like in the case of the Earth, for example, so then you can generate energy from that. You can have synchrotron emission from these kind of objects, and that's what is really pulsars. Pulsars are those neutron stars where the magnetic field is misaligned with the rotation axis. So the radiation mainly comes in the radio frequencies, because the synchrotron emission has the maximum emission in these radio frequencies. So that's the regarding the magnetic fields.
One clarification: whether the magnetic intensity of the star is also changes as in the evolutionary stage, starting from the protostar and as it evolved.
Good question. Usually no. It's assumed. To be frank, none of the stellar evolution models take magnetic field into account. So this magnetic field doesn't play a role in stellar evolution. So it is taken as conserved. The field is conserved. So where the magnetic field really takes a role in the formation of the stars, in the molecular clouds, the magnetic fields play a role in concentrating the mass into the stars. But in the stars, they conserve the magnetic field.
Mayya, you can also see some of the questions in the chat box.
I can see the blue jeans chat box. Are fast radio bursts related to any
questions are continuously coming via in the Facebook as well as in the chat box. Okay, you can.
Yeah, Facebook I can't see, but I can see here.
Yeah, I will pass on. I will pass on. In the meantime, you can
Mhm.
see the question in the chat box.
Are fast radio bursts related to any stellar formation? No, no. Fast radio bursts. Sorry, I haven't understood the question exactly what they are. Is position of black hole changes? Where? The question is not clear.
Yeah, our fast radio bursts are related to any stellar formation.
Yeah, the radio bursts. No, they are completely different phenomena. So right now, it's not part of stellar evolution. So
Okay.
any other question there in the?
Yeah. May I pass on the question asked in the Facebook? How black holes affect the speed of light when it is absorbed into it, since the speed of light is universal? Asked by Romin P. Roy.
Well, black hole doesn't change the speed of light. Speed of light is universal. So is life really exist outside our solar system? Nothing related to what I gave, but I assume it exists, but there is no evidence for its existence yet. So we know that even if it exists, getting the evidence is not easy. So definitely, I mean, in the last decade or so, a lot of planets are being discovered in the in different other stars. We have around more than 3,000 planetary systems in different stars. So and most of the, I mean, some of these planetary systems have planets that can have water, water in the form of liquid, so which we call as the conditions suitable for life. So life can exist, but they are far away, the stars, and there's no way we can really see that life exists there. I want to know something about white hole. So this question by Harshavardhan Bist. Well, the white holes doesn't exist. It's only fiction. So as far as astrophysics is concerned, white holes doesn't exist. Any more question there in the Facebook?
Can you explain something regarding the limiting radius of the neutron stars, that is square radius?
The neutron star radius is not square, so it is the radius. So that is determined basically by the pressure exerted by the neutrons. So that is what resists against the gravitational potential. Gravity will always compress the material. So, but the neutron star pressure originates basically from the Pauli's exclusion principle, where you can't push the fermions further inside, so that exerts a pressure, and that pressure counters the gravity, and for a given mass, so you can have an exact radius. So the radius can be calculated quite exactly. That's why we know the radius. And there are a few cases where recently radius is really measured. So again, they are very compact. We can't take images of neutron stars, but using some technique recently, radius have been measured as like 10 kilometers.
Now there is a question regarding is time different inside black holes?
Well, inside black hole we can't see, so it is completely in the theoretical regime. So I don't know.
Okay. If there are no questions, probably we can wind
Any
up.
direct question? If somebody wants to ask direct question.
Yeah. Um, how does the radius and mass of black holes related? This is
Well,
from how does the radius and mass of black hole related?
well, as I mentioned, black holes does not have a radius. So entire mass is confined to a point source. What we call as a radius is the square radius, and the square radius has this formula where the radius is proportional to the mass, linearly proportional to the mass. Radius is 2, the gravitational constant, times the mass divided by the c square. C is the speed of light. So that's the exact formula for the radius of the event horizon.
I have one question from the Facebook. A black hole, how the Hawking radiations are emitted from the black hole?
Sorry, again, questions are about the things that I haven't covered, and I don't work on the Hawking radiation at all. So completely on the theoretical side, these questions.
It is not regarding stellar evolution and the structure of galaxies. Now, regarding the galaxy structures, there are the various type of galaxies, lenticular and then elliptical. And what decides these structures? Why these variability?
Yeah, exactly. So I had that. I removed that finally. So yeah, our galaxy Milky Way is a spiral galaxy. There are other galaxies known as elliptical galaxies, and I think I have one. So there are elliptical galaxies and there are irregular galaxies, and the lenticular galaxy, which I don't put it here. So one of the interesting fields of study these days is exactly to find out why you have only these 3 or 4 kinds of forms in galaxies. So basically the fundamental parameter that decides whether a galaxy will be elliptical form or disk form is the star formation rate that galaxies had in the beginning. How fast stars are formed. If the stars are formed very fast, it will turn into an elliptical galaxies. If the star formation in the beginning was not very high, then it will have one of these forms, spiral or this irregular shaped. And finally, these all spiral and irregular galaxies will merge together because galaxies are interacting always, and the galaxies are not finished products. They keep on growing in size. Each time they grow, and by growing they can also change the form. A spiral galaxy can convert itself into a spherical galaxy like an elliptical galaxy. Lenticular galaxies are in between. They have a small disk and a very big central portion which you call as bulge. So there is evolutionary trend in the sense that as time goes on, more and more galaxies will interact and they form all into elliptical galaxies. That's a short description of what we know regarding these different types of galaxies.
Now in the Facebook, Joyce and Emmanuel has asked, is there any chances that the radius of planets will decrease to less than Schwarzschild radius?
Well, it's easy to calculate. If you calculate the radius for a Schwarzschild, Schwarzschild radius for a planet, so you will find that it can't. So you have to compress all the mass into less than a size of probably a coin, so that it is a black hole. So for every object you can find the Schwarzschild radius, but usually the Schwarzschild radius is much smaller than the object size, so you can't do that.
Okay. Uh,
Okay.
Okay, let us wind up, Maya.
Yeah.
I have to thank Professor Divakara Mayya. You have began with the fundamentals of stellar evolution, and then Green's law, the color sequence, and then you took us to various evolutionary stages up to the black hole.
Last winding up.
Yeah, in almost 1 hour, you have touched almost all the points, and you also spoken regarding the uh, discovery of gravitational waves and also the challenges uh, in the frontier area of astrophysics. And we can continue, but you have to be for a good sleep. You are almost now it is midnight in Mexico. Uh,
ಪೆನ್ ಡ್ರೈವ್ ಹಾಕಿಲ್ಲ ಇದರಲ್ಲೇ ಕಳಿಸ್ಲಂಗ್ ಇದೆ ಇದರಲ್ಲೇ ಕಳಿಸ್ತೀನಿ ಡಾಕ್ಯುಮೆಂಟ್
thank you very much, Maya.
Okay, thank you. It's midnight here, so it's a good time to wind up. Okay.
Yeah.